Hello everyone, welcome to another session of the Learning Glass. Today we'll talk about psychrometry, which is a way to analyze mixtures of air and water vapor. And the big application of this is for mechanical engineers for HVAC, where they are using heating and cooling systems for air conditioning and heating purposes, and many times they have to consider the water content in the air, the humidity. So on Earth, I guess this psychrometric chart at least is based on the assumption, or this particular chart that we work with in this class is saying that the pressure of the atmosphere surrounding the device, the system that you are analyzing, is at 101 kilopascals, which is 1 atmospheric pressure, which is pretty typical of San Diego because we're close to sea level. And then in terms of psychrometry, this is a common analysis for the learning when you're using the standard initial chart. Another assumption is that when you're designing a system with air and water vapor, that in most applications, at least that we're going to learn, is that the mass of the dry air, let's call it A, and it doesn't change. It's a steady flow in terms of dry air. So with those two assumptions, we can use this psychrometric chart to get some very nice, relatively fast results in terms of energy balances and properties of this flow. Okay, so the chart itself has a lot of variables on it. It might take a couple looks to get used to it and get a feel for it. And it looks like this thing here has this funny shape, kind of like a shoeish. So this has many axes, even one over here. So what this chart is capturing is properties of a dry air plus water vapor mixture. There's a dry component, but then in the gas, there's water there. So it's a uniform mixture. There's some water vapor in there. And to keep track of the properties of these average, like it's a mixture, so it has an average properties, this chart helps to keep track of that. And this left axis here is omega. And the book gives you kilograms of vapor over kilograms of dry air. Some give grams just because it's an easier number to work with. So the typical chart says that at 1 atmospheric pressure, the maximum kilograms of air, vapor is 0.03, so like 30 grams per kilogram, and over here it's about 2 on the low end. So that's the typical loading of vapor that we deal with in a lot of our applications on Earth. And so this is what we're going to use on the chart, but it's similar to this partial pressure of vapor. It's related to that. This is telling you what's the vapor of water, the gas phase water that's in the air mixture. The bottom axis tells you temperature, but normal temperature, what we call dry bulb, which is what your thermometer would read without any modifications, or what your cell phone reads, iPhone temperature reading. And I forget if this is going to be like 60 Celsius or so, I think, degrees Celsius. And and then within this body of the chart, there are these lines. For example, if there's a line here, there's many lines kind of going along with these, and they're lines of constant relative humidity. So this particular line on the chart goes through the middle, and all along this line, the relative humidity is 50%. So at a certain temperature if you go up to intersect this line, it'll tell you the relative humidity is 50%. So depending on where you are in the height, you'll intersect with different relative humidities. Another line here goes kind of like this, is the specific volume. I shouldn't make it that big. It's a little v, baby v. Another line that goes is, so if you were to go up, this would be constant temperatures. That's constant temperature lines. And then if you intersect with this axis here, there's two things with this axis. That this is your temperature of the wet bulb, meaning that it has some information about the water, the gas phase vapor, because this wet bulb is you're taking a thermometer reading that's surrounded by saturated water gas phase. And that tells you something about the humidity. And this line here, when this line, the reason why this is kind of the same shape as this is because this is the saturation line. Okay. So where this comes into play when you're talking about, if you're analyzing a system starting at some state at the inlet and another state at the outlet, we need this because we can apply the first law of thermodynamics to this and get some energy balance and make a device with some work out transfer and some heat transfer for some applications potentially. And this chart has that, but it's this axis here, kind of outside of the chart, and there's constant lines on this chart as well, leading to the enthalpy axis, which is up here. So it's about 10 here, 100 here. So the unique thing about this is that the units of these enthalpies, it's saying that you have this is the enthalpy of the mixture of vapor and dry air. But it's normalized by the amount of dry air. Why? Because you can assume that the mass of dry air stays constant. So even though you might have a process going from a high omega, a high mass loading of water vapor to a low mass loading of water vapor, meaning some water left in between this change of state, it left it into a different stream. The enthalpy can be tracked easier if the mass of the dry air stays constant, and it allows you to simplify this analysis because you no longer have to keep track of the enthalpies. It's a faster way to keep track of this enthalpy change. So again, I wrote down some of the parameters, but what we're looking at here is the enthalpy, kilojoules per kg dry air, the mass loading, omega, kilojoules of vapor over the kilojoules of dry air. We have temperature of the dry bulb in degrees Celsius, temperature of the wet bulb in degrees Celsius. We have V, specific volume, and that's also little v. What the units are is cubic meters per kilogram of dry air. There's also phi here. So all of these parameters of the mixture of the state of this system, which is atmospheric air, moist air, a mixture of vapor and dry air on this chart. So that's good. Okay, so let's do an example to show how this is used. So I'll race up here. So let's say this is cooling. With dehumidification. So some of the water leaves the system. So you can think of a channel where this process occurs. So you would have some flow coming in. I'll get that. And this flow will get exposed to cooling coils. So this inlet would have a certain mass flow in, dry air plus vapor in, and the inlet has some temperature in, and it has some omega in, which is similar to some omega relative humidity. Then it gets exposed to these coil, and because it gets cooled enough, it reaches the dew point. Or another way of saying that is that when this mass of water vapor that's in the air, the partial pressure of that, it is exposed to a temperature that is colder than it started. That temperature reaches the same temperature, which matches the same temperature which the saturation pressure at that temperature on the steam table is the same as the partial pressure of that. When that happens, you have condensation. You reach 100% relative humidity. And the water condenses out of the mixture stream. And so that's what happens when you're when you cool it enough with some finite amount of heat transfer. So this would be some Q out of your mixture, out of the mixture into the cooling coil. And at the end, you'll have a mass of the air is the same. But you have liquid water here. You'll have some vapor over there as well. And depending on the situation, in this case, we know that we're going to stay at the saturation. It's going to be 100% saturation, but the actual mass in this stream is less than what you started off with. Why? Because some of the liquid is in another stream, a separate stream, that is with the condensed water. And of course, from our intuition, T2 is less than T1. So stuff like that. Like this is the one situation that can happen. And this one is kind of intuitive, where we are starting at some certain temperature with some gas phase water that's stable. If we cool it enough, we're going to get condensation. That's what happens to our cold beer surrounding this. So that's in the air surrounding the cold beer reaches its dew point, or it has the partial pressure around the beer. The temperature drops, so that partial pressure reaches the saturation pressure because the temperature drops. the pressure didn't change, the temperature changed. Okay, so to analyze this problem, we'll first realize that water comes in at some certain mass, a certain omega. Then when you condense, water leaves in a separate stream as a liquid, compressed liquid, or a saturated liquid. Then the rest of the water stays with the gas phase, but so that's where the balance is. You start off with some water, some of it leaves this way, some of it leaves that way. So you need to keep track of that balance to solve this problem. So for mass balances, for the dry air, MA1 equals MA2, as usual for all of our analysis in this class. For water, in this case, it's different. The mass, so what's coming in? So first off, it's steady. So coming in, mass of the water in equals mass of the water out. I can put the summation here. So that means we have to keep track of all the streams coming in and out. This is one stream coming in, one stream coming out. I should make an arrow here actually. I'm pointing at some water, but what's happening is you have some mass out. And okay, so that stream is coming out, this stream, so what's coming in is you have the mass, we label it V1, that's coming in, equals this flow rate, let's call it M liquid, some stream of liquid water. That's another stream that's coming out is the outlet of the dehumidifier, the cooled saturated stream that has some vapor content still remaining in the air mixture. So that's your mass balance of water. Okay, now let's do the energy balance. So that's given by the first law, of course, and then, so the first law for a flowing system is for each stream you have some mass flow rate and some enthalpy of that stream. So you take the difference between the inlet and outlet streams, so that will be your change of state. That's balanced by some temporary energy transfers. So that's your first law. In this case, there's no moving boundaries. We're not going to consider fans or anything that are in there, or any compression or moving of the walls. But there is some heat transfer, of course. And then expanding these terms out and switching this to Q out, we would get the first law balance is Q out at some rate is the mass of dry air this is So notice that this is, I guess I skipped some steps here. And what I did was, as I put this in psychrometry chart notation, because the enthalpies that belong to the state 1 and state 2, these enthalpies have water in them, but the chart keeps track of this per mass of dry air. So that's unique there. So I skipped some steps there, so let me show you. I'll put it up here. So so this is accurate because we're using the chart, but if you wanted to be, if you didn't have the chart and you needed to keep track of things the standard way we treat this mixture, you would have had that there was some heat transfer out, of course, and then what's coming out of this system is one stream of liquid water and a stream of moist air. So that liquid water would stay the same. There's some flow rate of liquid water times the enthalpy of the liquid water. So this is all water properties. But there's another stream coming out, which is the mass of the dry air plus the mass of the vapor at the outlet times the enthalpy of the mixture at the outlet. So that's what's here. That's true. It's just harder to analyze. And then the similar in the outlet, you would have to say, okay, the mass of the dry air plus the mass of the vapor in the inlet times the enthalpy of the mixture in the inlet. So that's the first law. First law balance using, a standard way that we do these mixtures. The only reason why I did it differently here is because we have the chart, psychrometric chart. And that's easier because this enthalpy of the mixture is kilojoules per kg mixture. We would have to first take the average of these enthalpies, where enthalpy of the mixture equals the mass fraction of air times the enthalpy of air plus the mass fraction of vapor times the enthalpy of vapor. So that's how you do these mixtures. It can get pretty tedious pretty quickly. So that's how you would apply the first law balance. But thankfully, with the chart, if you get enough practice, you can see that this is a quicker way to do this because we have the chart. Okay, so how would you use a chart? Well, it depends on what you're given, of course. Okay, so let's say we are given in this problem that we're given a volumetric flow rate, let's say big V dot equals 280 meters cubed per minute. Okay, we are given that T1, the temperature at the inlet, equals 30 degrees Celsius, pretty hot. We are also given that the relative humidity is 50% at the inlet. So that's good. And then at the outlet, we're given that T2 equals 10 degrees Celsius, which is cold. And we're told it's saturated at the outlet, which makes sense because if we have condensation, then it's going to stay saturated unless the temperature changes or something. So that's what we're given. So then from the chart, we can start looking at the chart. So this chart is very useful because as long as we know two independent variables, those are the degrees of freedom that allow us to constrain the whole system. So in this case, we have three independent variables. Some of them are more useful than others. These two, I would say, are the most useful because this is not directly on the chart. It's useful, but it's not on the chart. So what these two allow us to do is to find everything else. So if the temperature is 30 degrees Celsius, the relative humidity is 50. I said that this is the 50 line here. So somewhere along this line, we have our state. So I would say 30-ish is around here. So state 1 is somewhere right here on this chart. So that'll allow us to extract all these parameters like omega is here, that's 1. Phi 1 is there. This volume can be extracted. The enthalpy can be extracted. So from the chart, if we know two of the variables, that gives us that H1 equals 64 kilojoules per kilogram of dry air. Remember that we're using this chart. Another thing that the omega from this chart following to this right axis. So this is gram of H2O per kilogram of dry air. And V1, little v, we'll show you why that's useful in this case, is 0.8775 meters cubed per kilogram of dry air. So those are the useful things for state 1. For state 2, we're at 10 degrees, somewhere around here, and it's saturated, so it's this line here. So if we follow this line, we're at state 2. That'll give us a different omega. That will give us different properties. We'll get the enthalpy. So for state 2 is 30 omega 2 Okay, so that's everything we can pull from the table, which is very useful. And because we're off the table, we already found enthalpy 1. It's a different number than this, but because it's normalized per gram of dry air, and as long as the dry air stays the same, it'll balance out. If we take the difference of these per gram of dry air, we'll get the same answer as if we took the mixture difference, if we did everything right. So I'll erase that. This is possible to do, but the whole point of this chart is to make things faster. Okay, so we pretty much have a lot of things except, okay, what is the mass of dry air? Well, we'll do a dimensional analysis, some units tricks, and what that is, it's this big V that we're given divided by the little v. So it is, we're given this 280 meters cubed per minute divided by this 0.87 blah 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 meters cubed per kg of dry air. So if we know the volumetric flow rate, and if we can find the density-ish, it's the inverse density, those units will cancel out for the volume, giving you mass flow rate. So that is per minute. So that's based on getting the state from this volumetric chart, the psychrometric chart, not from doing this, using these equations based on the ideal gas law, basically, which is possible, but if we have the chart, we don't have to. Okay, that's good. So that's this variable here. We have, from the chart, we pulled out H1 and H2 per mass of dry air. That's good. Okay, so from the mass balance, did I just erase it? Yeah. We can find the liquid flow rate, which I could write again. The liquid flow rate equals the mass coming in and the mass coming out of the vapor. And from the definition of omega, it's the mass of vapor over the mass of air, dry air. So another way to keep track of this mass of vapor is to say you can take the change. So the mass of the liquid is balanced by some change in the vapor, which you can express by the change in omega. This is liquid. So that's the mass balance for water, which helps you to find the mass of the liquid. And if you have the psychrometric chart, you can find that this way. Okay, so that's here. All right, what about this enthalpy of the liquid? Well, so these are the three streams. There's one coming in, some liquid water coming out of the system, and some moist air leaving the system at a different state. This liquid water is a saturated liquid, so this H liquid equals the saturated liquid property. So H liquid equals H saturated liquid at T, some T2 most of the time, from steam table. So if you know the pressure, which in these applications it's 1 atmosphere, you go to the steam table for 1 atmosphere at T2 of your problem, you find the enthalpy of a saturated liquid from the steam table. That's the energy, the enthalpy at that point. So in this case, from steam table, did I lose that again? Yeah, saturated liquid at 10 Celsius. (10 degrees Celsius), equals 42, I believe-ish. (42) per kilogram of water. Because that's the steam table. It's not the psychrometric chart. It's a normal per mass of that substance. And as long as we're taking the mass of that matching substance, that will work. And that's how this chart is. It's per mass of dry air, per mass of liquid. So that's good. So even though there is water vapor in these mixtures, that's accounted for if you use a psychrometric chart. So that's everything. If we were to plug in some of the values from the chart, we do this mass balance to get us the liquid mass, then we know that this stream of condensed water is saturated liquid. We can look at the steam tables to get the enthalpy there, and that's pretty much what we needed. So plugging all of these in, you should get that this enthalpy, this heat transfer from all these balances is something like this. After all these balances, it's 10,500 kilojoules per minute. So it's not in kilowatts, it's per minute. So that's how this balance would work. And that's how the psychrometric chart works. Well, instead of having a mixture that we would do these averages for, which is a valid way to do that, and we know how to do that because we have kept track of these mixtures before. In the psychrometry application, the chart itself is assuming that the mass coming in of dry air is a mass coming out of dry air. And the rest of it, if there's any other streams coming out, it's pure liquid. That's what we did there. So as long as we can keep track of those mass balances, and we can somewhere keep track of the enthalpy change based on the mass of dry air, this chart is very useful, because instead of finding these average values, we were just able to pull the numbers from the chart. Why does this chart work? Another reason is because if you know two independent variables, you can pin down all the other parameters. So that's one application of this. There are other situations where the psychrometric chart is helpful, like for heating and so forth. So with that, we'll just continue on another example next time. Thank you. Okay,